Everyone, welcome back. So we're working our way to learning how to solve for the internal forces and trusses. So we need to set up some sign conventions. First off, if you see the force, like if we cut a member, like we do our free body diagram thing, we have some truss. We say like, well, what's the internal force in here? And so I get rid of everything else. I have this little member, and then we figure out what the direction the forces are going. They're always going to be in opposite directions on either side. So they're pointing out or they're pointing in. But what is this called? Well, if the forces are pointing out, it's tension. If the forces are pointing in, it's compression. And as a note, compression is usually considered negative. That means in your free body diagrams, just always draw the arrows pointing away from the member. If you cut somewhere, draw the arrows pointing away from the member. Because when you solve for them, if you get a negative number, you just know it's compression, and you leave it as a negative number when you put it into the Moodle or something else. The last thing, which we're not going to see, at least not right now, is this, where you see there's a force that's applied, crossways on a beam. These members that we're looking at, they are two force members, which means they go, they're only along the line of that member is there a force. This bending thing throws that off. So that'd be what's called a three-force member, or multi-force member. And we'll learn about that later, but not today. So we're not going to see that for what we're learning about today. Now, what are some assumptions we're having to make to be able to solve these problems? Well, first off, we're saying they're all on the same plane. Now, in real life, there's going to be some variation, but it's close enough that it'll still have good accuracy. We said the loads and reactions are applied only at the joints of the truss. This is the only way we can have two force members. So we're not going to have any members with a load applied towards the center. We said the truss members are connected with frictionless pins, which you're like, wait a minute, what? Yes, I know that's a bit unrealistic, but what we're getting at is that if we're looking at our truss, these pins right here are unable to resist a moment. So without forces to protect it, it will bend and twist, which, considering the size of the members and the size of the pins, that's fairly accurate. All members are straight, no curvy members. And the line of action of the internal force within each member is axial. It means that it goes along the length of it. Whatever direction that member is pointing, that's the direction that the forces that go through it are pointing. The final one is that the change in length due to tension or compression is not enough to really mess up the geometry, which would also be true in most cases. These are all small members, so their weight is negligible unless I specify otherwise. Okay, so there are two methods for analysis. The method of joints, the method of sections. We're going to learn about the method of joints next time. But I want you to know that there's two methods. They're both very, very important. One involves looking at the place where we connect all of our devices together. The other one looks by cutting the members in half and seeing what happens on the inside. So, talk about this more the next time. We'll jump into method of joints. But thank you for listening, and I'll see y'all soon. Bye.